with chapter 4. A reminder, as I put an announcement the other day, I posted a recorded lecture to try to keep us on pace-ish. So I'm going to pick up from where that recorded lecture leaves off. So again, if you haven't watched it, make sure you do watch it. You're responsible, obviously, for that material that's on there. So what we talked about in that sort of recorded lecture for you guys was really the experiments that led to our understanding of the structure of the atom and the important experiments and sort of the modern version of the atom, which basically is that the atom is made up of mostly empty space. There's a dense positive core, which is the nucleus, and later experiments obviously determined that protons, which are positively charged, and neutrons, which have no charge, are obviously found within the nucleus. We have electrons, which are negatively charged out from the nucleus at some distance, flying around in a sort of random sort of pattern, as we'll talk about really in the next chapter as well. An electron sort of pathway is sort of unpredictable. There's sort of uncertainty associated with it. The more you know how it's traveling, the less you know sort of its location, and vice versa. That's what's commonly referred to as the Heisenberg uncertainty principle. Most of the mass of the atom is made up of the nucleus, which has the protons and the neutrons inside. The other things that we kind of covered in that little lecture there was the idea of atomic number. And the atomic number is the number of protons there are in an atom. And the atomic number can be found on the periodic table, and it is the number that typically is above the symbol. And it will tell you the number of protons that there are in an atom. Obviously, if we are dealing with a neutral atom, the number of protons will also equal the number of electrons, because in an atom, right, there's protons which are positively charged, electrons which are negatively charged, and there's obviously neutrons which have no charge. So if it is neutral and you have a certain number of positively charged protons, it does need to have an equal number of negatively charged electrons to balance it out. And again, that number can be found on the periodic table. Once again, if you look at the periodic table and all the numbers that come above the symbol, there is no number that repeats. So every individual element has its own atomic number of protons, which means as we think about protons, electrons, and neutrons, which make up pretty much the atom of most elements, it is the protons that's most important in determining what element you're dealing with, because every single element has its own number of protons. The other important number that we talked about is the mass number. And the mass number is the number of protons plus the number of neutrons. So the mass number will tell you how many protons and neutrons there are in an atom of an element. It is also important to note, as we talked about in that lecture, you do not find the mass number. It is not the bottom number. That is the atomic mass, not the mass number. So the mass number is not found on the periodic table. One easy way to remember that is when you calculate the atomic number, the mass number, number of protons, electrons, and neutrons, they all should be positive whole numbers. So if you look at the periodic table, pretty much every number underneath the symbol, they're all decimals, so they're not whole numbers. So they should never be taken from the periodic table as the mass number. We'll talk about what that is, obviously, which is the atomic mass. What confuses people sometimes, as we talked about in that lecture, is a lot of times the mass number and the number that you see sort of on the bottom of the symbol are numbers that are very, very close to one another. So sometimes people think they are the same, but they are actually different. From the actual problem, if you're doing some type of problem like this, you will have enough information to figure out how many neutrons there are, or how to figure out they'll give you the mass number, which will tell you the neutrons, and or you'll have the neutrons. You can then calculate the mass number. So really the only number you can get from the periodic table there is the atomic number of protons that's above the symbol. And a reminder as well that the definition of the atomic number is just the protons, not the electrons, although in a neutral atom, it'll tell you the electrons. Using both of these numbers together allows us to take the mass number and subtract it from the atomic number. And that is the number of protons plus the number of neutrons, and that is the number of protons. So when we subtract them, that is basically the way that we could calculate the number of neutrons, to take the mass number minus the atomic number, and that will get you your number of neutrons. We also talked about isotopes in that lecture. Isotopes are really the same element, but they have different masses. And as I just mentioned, it is the protons that basically determine what element you're talking about. So in order for them to still be the same element, they will all have the same number of protons. So what gives them different masses is they have different numbers of neutrons. So isotopes are basically the same element. They have different numbers of neutrons. The result of that is they obviously will have different masses because they have different numbers of neutrons. When we talk about protons, electrons, and neutrons, the proton and the neutron are about 1,800 or so times heavier than any electron that's flying around, with actually the neutron being slightly heavier than a proton. So it is the mass of that neutron as they change gives the overall mass of that isotope different. We do write sort of symbols for isotopes a couple different ways. One way is we use the symbol, and on the top left, we write the mass number. And on the bottom left goes the atomic number. Another way that we sometimes write a symbol that includes one of those things is something like this, where this number here is the mass number. So sometimes people will write a symbol dash a number, and that number that they give you is the mass number. Once again, we know that because if we go to the periodic table, we can see copper's number 29, which would be its atomic number and the number of protons. Any questions on any of that stuff there? Okay, so let us take a look at some here. So for each of these, we want to figure out the number of protons, electrons, and neutrons that there are in each of these guys. So once again, the top number here is our mass number. Bottom number here is our atomic number. And if we look at this, that will tell us once again the atomic number, which is the number of protons here in cobalt. This guy would have 27 protons. And because it does not have a charge, and we do know it doesn't have a charge because frankly, there's nothing written there. And if it did have a charge, that's where we would see it. So since we see nothing written there, we could assume that it's neutral. And as we talked about, obviously, if we have 27 positive protons, we would also need 27 negative electrons to balance it out. So the number of electrons here would be 27, 27 positives, 27 negatives, gives us an overall charge of 0. Our number of neutrons in this case would be our mass number, which is the top number, 60, minus the atomic number, which is the bottom number here, which is 27. Looks like a 33 there. Any questions on that there? All right, so once you finish the other two there and see what you come up with, protons, electrons, neutrons in each of those. Let's take a look here. Second one there is chlorine. So once again, we'll start with our protons, which is the bottom left number. So our number of protons in this case would be 17 positive guys. Once again, there is no charge written there, so we assume that it is neutral. which means we need to have a balancing number of electrons, which also should be 17. Once again, that's going to zero us out to no charge overall. Our number of neutrons here will be our mass number, which is the top left number, which in this case is 37, minus our atomic number, which is the bottom left number. So once again, that is our protons plus neutrons minus our protons. And that gets us 20, it looks like, in that particular case. Any questions on that there? Lastly, U, which is uranium. Once again, we're going to start with our atomic number, which you can find from the periodic table. That is 92. So this has 92 protons. Number of electrons in this case, again, because there is no charge, will balance out as well to 92. And our number of neutrons, taking our mass number, which was 238, minus our atomic number, which was 92, gives you a lot, like $1.46 maybe, something like that. Any questions on any of those there? Okay, so I want to try a few more here just to make sure. All right, so for each of these, why don't you write the symbol with the mass number and the atomic number? So periodic table will be helpful probably. Krypton has 48 neutrons, nitrogen has 6 neutrons, and we have iron with a mass number of 56. How many protons, electrons, and neutrons would there be for that one? Okay, let's take a look, see how we're doing. So krypton there is Kr would be our symbol. Once again, we could go to the periodic table and find Kr. We'll also see a number above it, which is important because that's going to be our, bless you, atomic number. So that atomic number in terms of our symbol will go bottom left, which would be 36. In addition to being the atomic number, it also is the number of protons, which is kind of the same thing. That's important because they gave us the number of neutrons, and those are the two things that we need to figure out the mass number. So once again, here our mass number will be our number of protons, which was 36, plus our number of neutrons, which was 48, gets us 84, I think. And that would go up there on top left. Any questions on that there? Looking at the next one, nitrogen, which is N. Once again, if we go to periodic table, we can find some helpful numbers. And obviously 7 would be our number here, which would be our atomic number. That is going to go to our bottom left. Taking our number of neutrons and protons will give us our mass number, which would be in this case 6 plus 7 gets us 13, which should go right up there on top. Once again, if you take the top number minus the bottom number, it gives you the number of neutrons, right? And lastly, iron, which is 56. Iron 56. So iron is Fe. We go to periodic table, we find Fe, and we see number 26 above it. And again, that's going to be our atomic number, which will go on the bottom, 26. In this case, they gave us the mass number, which was 56. Knowing the atomic number tells us in this case that this has 26 protons. It will have a matching number of electrons since it has no charge. And in this case, our number of neutrons will be our mass number minus our atomic number, which looks like it will be 30 in this case. Any questions on atomic number, mass number, protons, electrons, and neutrons? Now, what happens if we did have something that had a charge? So if we did have something that had a charge, those are again what are referred to as ions. Those are things with charges. And there's two types of ions. There are cations, which are positively charged, and there are anions, which are negatively charged. And if any of these guys, for example, did have a charge, so we take something like, we'll do our nitrogen there. Let's say it had a -3 charge. We'll keep all the other numbers here the same. Now, in this particular case, we would still look at our atomic number, and that would tell us that the number of protons here would be 7. The number of neutrons in this example would still be 13 minus 7, which would be 6. So clearly it's not the protons that change when something gets a charge, and it shouldn't, because as we just talked about, the number of protons tells you what element it is. So if you change the protons to give it a charge, you are changing the element, so it's no longer the same element. So protons stay the same. In this case, neutrons stay the same. So what really changes when something gains a charge is the number of electrons. So the number of electrons change. And in this particular case, this guy has now a -3 charge. And typically the minus charge means that something has gained electrons. And the number of the charge is how many electrons it gained. So this guy gained actually 3 electrons from the neutral guy, which means in this charge, he would have 10 electrons. 7 positives, 10 negatives leaves you a -3 left over. And again, that is where the charge comes from in this case. Any questions on that? And if we compare our neutral nitrogen that we got up there to our guy with a -3, again, the only difference here is it has 3 more electrons. And that's what happens with anions. Anions will gain electrons. And they are typically nonmetals that do that. Now, if we took our iron and we did iron here with a +2 charge, we'll do the same mass number there. In this case, once again, it would have 26 protons. It will once again have 56 minus 26 for 30 neutrons. Once again, it is the electrons that change here. So in this particular case, it has a positive charge. So when you see a positive charge, it means that somebody has lost electrons. And what that means is it now has more protons than electrons. So it becomes positively charged because it has more protons than the negatively charged electrons. And the number tells you how many it lost. It is 2. So it lost 2 from the neutral, and it would actually have 24 electrons. 26 positive guys, 24 negative guys, leaves us a +2 left over. And once again, that is where the charge comes from in this particular case. So our cations are made by losing electrons. And that's how come, again, they become positively charged. And it's usually metals that actually do that. So if you have something with a charge, really the only thing that will change is the electrons. If you have a positive charge, it has lost electrons. And if you have a negative charge, it has gained electrons. The easiest way to figure out the electrons, if you're not sure, is if it has lost electrons, you basically take the atomic number, which is the number of protons, but also in a neutral guy, the number of electrons, and you can just subtract how many electrons it lost. So for example, again, our nitrogen there had 7 electrons to begin with because the atomic number was 7. And again, it gained 3 electrons because it's negatively charged. So you add 3 electrons, gives us their 10 electrons. And for our iron, it had 26 electrons to begin with. So if you take 2 off of the atomic number because it lost 2 electrons, gets you to 24. Any questions on things with charges, how they figure out protons, electrons, neutrons? Okay. So as I mentioned before, isotopes are basically the same element. They have different numbers of neutrons. In most sort of chemical reactions, it is the electrons that really take place and sort of do the reaction. Neutrons and protons are not usually involved. One nice thing about isotopes is they really do have the same characteristics with other isotopes of the same element. So sometimes isotopes are radioactive isotopes of a particular element. So you can, for example, if you were trying to follow a particular element through a pathway or something like that, you could use the radioactive version of it and it'll basically work the same way as a non-radioactive version. The benefit of that is you just follow the radioactivity and figure out where all, say, that element ends up through a pathway by just following radioactivity. So sometimes radioactive isotopes of elements are very helpful for that. And other things like, medicine and stuff like that, we use them as well. We're going to now talk about the periodic table officially. So that is a periodic table. Impressive. There we go. So a periodic table gives us obviously a lot of information about the elements, some of which we kind of touched upon here. Let's talk about some of the different aspects of the periodic table. First off, elements in a column going up and down on the periodic table, they're referred to as groups. You used to call them families occasionally, but not more so. Most people go with groups. And when you look at periodic table like the one up here, the one hanging over there, there's a lot of different sort of numbering that you sometimes come across on a periodic table. Sometimes there's something referred to as like the A numbering, the B numbering. Then there's just like 1 through 18 sometimes. In most chemistry classes, including this one, probably through this school and most schools, is the representative numbering, which is the A numbering. So we use usually the A numbering. And the A numbering means that group 1 is over here. This is group 1. Actually starts with lithium, not hydrogen. We'll talk why in just a second. Group 2 is here. We skip the middle. Over here where boron is group 3, 4, 5, 6, 7, and group 8. So those are the numbering that we use in this class. And like I said, most chemistry classes that you use is that A numbering. I'll be honest, most people don't use the A part of the numbering. They just say group 1, group 2, group 3. But in most cases, they're talking about the A numbering when they do that. So 1, 2, skip the middle. 3, 4, 5, 6, 7, and 8. Going left to right across a row on the periodic table is what is referred to as a period. And there actually are 7 different periods on the periodic table. Starting about here, 1, 2, 3, 4, 5, 6, 7 periods heading that way across the periodic table. So groups up and down, periods left to right on the periodic table. In addition, we've talked about there, the number up on top of the symbol is our atomic number, which is our number of protons that you have in an atom. The periodic table is also broken up into really 3 different categories. On most periodic tables, you'll see around boron, this sort of staircase that kind of comes down here. And pretty much everybody to the left of the staircase, including the 2 rows on the bottom, which is not pictured up here, but over there you can see the 2 rows where we have LA and AC. Those are all metals. Metals are good conductors of heat and electricity. They can be pulled into wire, hammered into sheets. They typically have a shiny appearance. For the most part, metals are solids at room temperature, except for mercury, which is why on a lot of periodic tables it's a different color. It's like blue up on that one. It's actually a liquid. Mercury, everybody else that is a metal is typically a solid. To the upper right of the staircase, this part, those are nonmetals, and on the staircase itself, they are referred to as metalloids, or sometimes referred to as semi-metals there. And let's talk a little bit about nonmetals next. Nonmetals are kind of opposite there of the metal characteristics. They're poor conductors of heat and electricity. They're dull, they're brittle. And unlike metals, nonmetals have a wide variety of states. So some come as gases, some come as liquids, some come as solids. A lot of nonmetals are those elements that come as diatomic molecules that we talked about, I think. Things like H2, N2, O2, F2, Cl2, Br2, I2. These are all diatomic molecules. And this is how these elements come naturally, and they're all nonmetals. And that is why I said earlier that hydrogen, which is right here, is not part of group 1, and that is because hydrogen is what type of element? Hydrogen is actually a nonmetal. Even though it's hanging out with the metals, hydrogen is a nonmetal. Hydrogen has some unusual properties, one of which is it's the only element that has a proton and an electron, no neutron. Other properties that are things like acids, it kind of behaves similarly to a metal and similar to what we see in group 1. So it behaves kind of similar like group 1 guys in that aspect of it, but it actually is a non-metal. If you're old like me, hydrogen used to be put a lot of times on periodic tables, actually on both sides. They would actually put it like over here as well. They don't do that too much anymore, but you used to see it kind of on both sides. In addition, our guys that are on that staircase itself are our semi-metals or metalloids. And again, kind of coming down, through here are our metalloids like silicone, arsenic, and so forth. The location of our metalloids or semi-metals, and some books throw boron in there as well, which is right here. The location of our metalloids does sort of make sense. Metalloids actually have properties that are very similar to both metals and nonmetals. So the same metalloid will have properties that are very similar to what we see in metals, and that same element will have properties that are also very similar to what we see in nonmetals. And it makes sense because as we go from left to right here, we're going from metals into nonmetals. So these guys sort of a transitioning point between the metals and the nonmetals. They also have characteristics that basically fall on both sides of that staircase. Any questions on that there? Couple other important things here. Some groups have special names. So starting with group 1, which once again is here and really here with lithium. Group 1 is the alkali metals. Right next door is group number 2, beryllium, magnesium, and so forth. Those are the alkaline earth metals. Coming all the way over here to group 7. Those are our halogens, fluorine, chlorine, bromine, iodine. And right about here, group 8, as we will see, those are our noble gases. So those are some special names that you should be aware of. The word alkaline means basic. So a lot of strong bases come from group 1 and group 2 on the periodic table, like sodium hydroxide, potassium hydroxide, calcium hydroxide, and so forth, kind of coming over. Those guys, when they combine with hydroxide, make some strong bases. Halogens, on the other hand, here, as we talked a little bit about, and I think next week you'll do an experiment. Part of the experiment will involve the halogens and looking at reactivity, but they are very reactive nonmetals. Reactivity in terms of nonmetals increases as you go up and to the right on the periodic table. They react with metals to form ionic compounds. A lot of acids also come from group 7, like HCl, which is hydrochloric acid, HF, which is hydrofluoric, HBr, which is hydrobromic, and hydroiodic acid, which is HI. There are actually a lot of strong acids. HI, HBr, and HCl are all strong acids. HF is actually a weak acid, but a lot of acids are formed from a result of hydrogen and those guys coming together. As you can see, fluorine is kind of a yellow gas, green gas for chlorine, brown sort of vapor for bromine. And you did that lab, I imagine, where you use the iodine and the whole thing turned purple through the sublimation, yes. And the evaporating dish with the ice on it now. So as I mentioned before, group 8 there at the end are their noble gases. Noble gases are chemically inert. They don't react with others. They're very happy the way they are. As we'll talk about when we talk about bonding, that's pretty much the goal of everybody, to achieve the same electron configuration as noble gases, because they are very stable, not like turn into the noble gas, but become like them in terms of their electrons, which makes them really, really stable. The two rows at the bottom actually should go on a periodic table. If you follow the numbering, they actually go right there. So as you can see, that is 57, then 58, and then that's 89, then 90. So those two rows actually should go right about there. I've never really seen a periodic table do that, because it'll make your periodic table very wide. I guess I shouldn't lie. I guess I've seen it once, and it was here at the old building. Took up the entire wall because they inserted those in the middle, and then it kept going. So those are sometimes referred to as lanthanides and actinides, because those are the elements that they should follow on the periodic table. The good news is we don't really deal too much with those guys. You might see them again in 1B. If you take 1B, when you do the nuclear chapter, chemistry chapter, a lot of those guys on the bottom are radioactive sort of elements. So, and also where we get the ones with the cool names, the better names like californium, isinium, all those kind of names are down there as well. Between group number 2 and group number 3 on the periodic table, which is basically, as you can see here, that is our transition metals. And transition metals, one of the characteristics that they have is, for the most part, they have the ability to make a variable type of charge, which means in certain cases, the same element can make different types of charges. They will be positive charges because they are metals. So like copper could be +1 or +2 in certain situations. Iron could be +2 or +3 in certain situations. So there's not like a fixed charge. Other guys on the periodic table outside of the transition metal region, a lot of them do have sort of fixed charges that no matter the situation, they're always going to be a certain charge. Like sodium, for example, always going to be +1 no matter what the situation is, or who it's attached to. But transition metals are a little bit different than that. Also, these guys just to the right of the transition metals, but below the staircase, they're actually metals where we have lead, which is Pb, Sn, which is tin. So these guys also, a lot of these guys down here can make multiple sort of charges as well. That's why also the 2 rows down here, which because they should go right about there, they are also sometimes referred to as inner transition metals, because they technically should go kind of in that spot as well. Any questions on that there? So obviously, the characteristic shape periodic table was originally put together to put elements together that have similar sort of properties. So typically, as you go down a group, they have very similar properties. And obviously, as you go across a period as well, they do share that. And as we go from left to right on the periodic table, we're moving more from a metal sort of characteristic up and to the right to a non-metal characteristic that occurs. In addition to our noble gases, which is group 8 there are some metals which are considered noble metals, which are virtually unreactive. So gold, silver, and platinum, which is most of those are there in the transition metal region. They're very unreactive sort of metals. That's how they test if your jewelry is real gold, right? They dump some nitric acid on it, which will do nothing to real gold. Fake gold do a lot to it, so it's not real in that case. So those metals are really reactive, like our sort of group 8 elements. So by the way, group 8 gases, unlike our hydrogen, nitrogen, oxygen, and so forth, they are what are referred to as being monoatomic gases. They come as ones. So unlike H2, N2, and O2. Also speaking a little bit about charges, just so we're clear, if you take anything off the periodic table by itself, uncombined, not attached to anything else, they do not have charges. So things just don't have charges. Things really only get charges when like a metal and a non-metal come together and electrons start to leave one and go to the other. That's when things actually get charges. But if you had like iron, piece of iron metal by itself has no charge. If you had chlorine gas, it has no charge. So again, things only really do get charges, you know, when they start combining. And obviously those are diatomic molecules that we talked about, which is a lot of our non-metals that occur there. Any questions on the periodic table? So clearly you need to know which way groups go, which way periods go, the proper numbering, and earth metals, halogen, and noble gases, where they're located. You know which elements are metals, which ones are non-metals, which ones are metalloids. Any questions on that there? Obviously where transition metals are as well. Okay. We're going to skip over this here. So since we talked a little bit about ions, let's talk about ions a little bit more here before we kind of close out on this chapter. There we go. So as I mentioned, anything that does have a charge is referred to as an ion. And there are two types of ions, cations and anions. And it is only a result of either gaining or losing electrons that we do get these guys with charges. So as we see here with our sodium, neutral sodium, which is atomic number 11, has 11 protons and 11 electrons, which gives you no charge overall. Our sodium here with a +1 charge will once again need to have 11 protons to keep it sodium. The plus tells us that we lost electrons, and the 1 tells us how many. So that would then take us to 10 electrons. 11 positives and 10 negatives gives us our +1 charge, which again is where that charge comes from. And that would be a cation. One way we sometimes can write an equation to demonstrate losing electrons like we see here is like in the equation that we see, we have our sodium that has no charge. It becomes sodium with a charge and 1 electron comes off. When we see an electron on the right-hand side of the arrow, which is the product side, that indicates that this guy is losing electrons, so it's like it's being given off as a result of that reaction that's taking place. Same thing if we look at magnesium. Magnesium, again, in a neutral sense, has an atomic number 12, which means it has 12 protons. It would also have, obviously, 12 electrons. Magnesium with a +2 charge will once again have 12 protons, but the positive charge means in this case, it actually only has 10 electrons. 12 positives, 10 negatives gives us a +2 left over. And that is what we see there with the charge. We also could represent it here by an equation. Magnesium with no charge, magnesium +2 electrons coming to the other side. It is a little misleading, and just so you know, electrons do not actually just all pop off at once. They actually come off one at a time. So something like magnesium, what would happen first is the magnesium would lose 1 electron and become positively 1 charged. Then that positively 1 charged guy would lose a second electron and become positively 2 charged. So electrons actually are lost one at a time, even though sometimes we think of them just all coming off at once. Actually, a stepwise process. There's actually a certain amount of energy required to do each of those steps, a certain amount of energy to pop off that first electron, a certain amount of energy to pop off the second electron. Which one would be easier to take off? First one or the second one? It is actually going to be the first one is easier to take off. The first one's neutral. So when we pop off the electron, does the overall atom get larger or smaller when it loses an electron? I'm just gonna keep moving my hands like this. When we lose an electron from like the electron cloud, it shrinks, right? The electron cloud. So all the electrons come in. Now those outer electrons are now closer to the nucleus, right? In the positive charge, which means the next electron is going to be held tighter, right? So it's going to take more energy to remove it. You take off the next electron, it gets even smaller, right? It gets harder to keep popping off electrons. So always easier to take off the first electron, then say the second, then the third. That's what is referred to as ionization energy, which we'll talk about at the end of next chapter, I think. And aluminum there had 13 protons to begin with and 13 electrons. And again, here with a +3 charge means it has lost 3 electrons. So aluminum here would actually have 10 electrons and 13 protons, and that's what gives it the +3 charge. When we go to name something that's an ion, 2 things. First off, if you're asked to write the formula for an ion, like a cation, it should have a charge. So like Mg2+, Na+, Al3+. If we go to name these ions, it's pretty simple. We just use the entire name of the element. So you just put ion at the end. So Na+ would be our sodium ion. So this guy here, Na+ would be our sodium ion. Mg2+ would be our magnesium ion. And even if you had something like H+, this would be the hydrogen ion. So anything that's positively charged, that's a cation, you need to give it a name. The good news is it's the same name as the element, and that's all you need to write is the element, and you should write ion after it because it does have a charge. And if you write the formula, you should include the charge as well. Any questions on that there? Now, obviously, an anion, as we talked about earlier, comes from gaining electrons. So since they gain electrons, they actually have more electrons than protons, which is really the result of how they get that negative charge. So something like chlorine with no charge has 17 protons and would have 17 electrons for a grand total of no charge. Cl- would still have 17 protons because it's chlorine. The minus means it gained electrons, so it actually would have 1 more electron. 17 positives, 18 negatives gives us a -1 left over, and that is how we get to our charge. We could also represent this with an equation. Since electrons are being gained, we put the electrons on the left-hand side of the arrow. Which is known as the reactant side. Like that chlorine is gaining that electron and now becomes negatively charged. So that is how we represent that. Now, when we go to name things that are negatively charged, it is a little bit different than something with a positive charge. We drop the last part of the name, E at the end of it. So our Cl- goes from chlorine to chloride, IDE at the end of it. If I had F-, which is fluorine, with the charge, it is now fluoride. But O2-, that's oxygen, and now becomes the oxide ion. So things with negative charges, ions, you drop the last part of the name, put the IDE. And again, as it says there, it is only the number of electrons that basically change the glyco charge. That is why when we put a sodium ion together with a chloride ion, one really important thing is individually when we write the formulas for these ions, they should have charges. But whenever you take something that is a positive charge and a negative charge and put them together, it should always end up equaling 0. the charge. And the easiest and simplest way to do that, in this case, 1 sodium with plus and minus 1 equals 0. So the correct formula here for this guy, when we put it together as a compound, would be NaCl. Has no charge, but it is made up of basically two things that do have charges. It's made up of a sodium ion with a positive 1 charge, chloride ion with a negatively 1 charge. We always want to put it together in the simplest way, gets us to 0. And so, for example, if I had something like Ca2 plus and Br minus, in this case, if I put these guys together, would I get an overall charge of 0? I would not, right? 1's plus 2, 1's minus 1. I actually need more of the Br. I need 1 more. And basically that will give me minus 2 to balance out the plus 2 that's here. And my formula would be 1 calcium and 1 and 2 bromines here. Yeah. And it would be CaBr2 would be the correct formula. That is the simplest way to put those guys together to get 0 charge. How would we name these guys? Same way. Na is sodium. Cl becomes chloride because it's really minus 1. So that is sodium chloride. Ca is calcium. Br is really Br minus, which is bromide. Calcium bromide would be the proper name for that guy. Doesn't matter that there's 2 of them, has no effect in that type of naming. We'll talk more specifics when we get to naming, but that would be the names that we would get for those guys. Any questions on that? So speaking of ions in the periodic table, as I mentioned, when things do start to combine, really metals and nonmetals, that is where we get charges. So there are things that have fixed charges. So everybody in group 1 makes a plus 1 charge. Everybody in group 2 makes a plus 2 charge. Group 3, really it's aluminum we're mainly talking about in most cases, is plus 3. Now there's that staircase that kind of comes down through here. So we actually skip group 4 and go to group 5. And group 5, we're talking about here are nonmetals like nitrogen and phosphorus. Those guys will make a minus 3 charge. Group 6 will be minus 2. Group 7 will be minus 1. So it goes like plus 1, plus 2, plus 3, skip. Minus 3, minus 2, minus 1. The minus is always the nonmetals above the staircase is what we're talking about. Once again, below the staircases, some of those groups are metals. So above is what we're talking about with our negative guys. These are the fixed charges. No matter what the situation is, that is their charge. It doesn't matter how many you put together or what you put together. Each individual guy will have that charge. Transition metals, as I mentioned before, can have variable charges. There are 3 exceptions, and that is zinc and cadmium. Both of those guys will always make a plus 2 charge. And if you hang a left there at cadmium, where silver is located, silver will always make a plus 1 charge. So those are 3 exceptions in the transition metal region that have fixed charges. Pretty much everybody else in transition metal region can make a variable type charge. And even as I was just talking about, outside the transition metal region, below the staircase, where you have things like tin, SN, lead, PB, bismuth, Bi, they can make multiple types of charges as well. So they have kind of variable type of positive charges. Any questions on that there? Super helpful to know, especially when we get into the naming chapter, the charges, so you can put everything together correctly. By the way, our good friend hydrogen here, technically has a fixed charge, but actually has 2 fixed charges. In most cases, hydrogen is plus 1. But if hydrogen should actually follow a metal, it will actually be negative 1. So if you have hydrogen after a metal like LiH, it's actually the negative version of hydrogen. Hydrogen is kind of like the only element that can kind of go both ways, plus and negative. Mostly is positive, but in some cases, when it comes after a metal, it actually is the negative version of it. Any questions on that there? Now, most pure substances are very bad conductors of heat and electricity. It is when we basically dissolve some substances in water and we form these ions that we actually get things that can conduct electricity really well. And they're known as electrolytes. So electrolytes are really things that when they go for a swim, they will produce some ions, and those ions being present help complete all the circuits and all that, and you're able to conduct electricity really, really well. Pure water is a really bad conductor of electricity because frankly, it has no ions in it. And once again, let's be very clear here. The water that comes out of your faucets, there is not pure water. There's a lot of stuff in there, including ions to clean it, which means you will electrocute yourself if you blow dry your hair in the shower. But if you have just pure water with nothing else in it, it's actually a bad conductor of electricity. But once you start adding ions to water, it becomes a good conductor of electricity and what are known as electrolytes. There's actually a few different types of electrolytes. There are strong electrolytes, which basically 100% break apart into ions. So if you had a sodium chloride solution, when it's really in that solution, what you really have floating around in there is 100% of the individual ions floating around. There is no longer any sodium chloride units still together. They have completely broken apart. And what you just did is generate a lot of ions really quickly, and it's going to be able to conduct electricity really, really well. An experiment sometimes people do is they take a light bulb, attach some electrodes, 60 electrodes in the solutions. And if it's a strong electrolyte, the light bulb will come off really, really bright. So it'll shine very, very bright because it's conducting electricity really, really well. And that's what you will have happen in a strong electrolyte solution. A very bright light bulb. Yeah. It conducts electricity very well. The other type of electrolyte is a weak electrolyte. And unlike a strong electrolyte, a weak electrolyte will mainly stay together, but will produce a few ions. So something like HF, for example, which is hydrofluoric acid, will break apart into H plus in solution and F minus. But mainly what you have in that solution is still the whole unit together. But because it's able to produce a little of these ions in solution, we still have the presence of ions being in that solution. So it's still able to conduct electricity, but nowhere near what a strong electrolyte could do. So if we take our light bulb example, the strong electrolyte will be a very bright light bulb. The weak electrolyte will turn on the light bulb, but it'll be very, very dim. But it's still able to conduct electricity, but it'll be very, very dim. So it still can conduct. How do you know sort of the difference, or if it's a weak electrolyte? One main way is actually the arrows. We have arrows that are heading in both directions, and that's very commonly referred to as a reversible reaction. That means that the forward direction, which in this example would be the HF breaking apart into H plus and F minus, happens. And at some point, enough H plus and F minus get made that they decide to recombine and head in the opposite direction, where the H plus and F minus will come back together and make the HF. Eventually, it will reach what is known as chemical equilibrium, but you basically have the reaction heading in both directions. And that's different than a strong electrolyte. It's like a one-way street. Everybody's dumping out to the right-hand side. Nobody's coming back the other way. Everybody's going and making the sodium ions and the chloride ions. And that's really the difference there between the two. Any questions on that? Also weak electrolytes in equilibrium, the entire Chem 1B topic of this year. Lastly here, non-electrolytes are things that will dissolve but produces no ions. So although they will dissolve, they will not produce any ions. And because they don't produce ions, they will not conduct electricity. So they will not conduct electricity. So something like sugar, for example, you put sugar in water, it will dissolve, no problem. But sugar is a molecular compound made up basically of carbon, hydrogen, oxygen, sharing of electrons. So it doesn't produce any ions. So even though it dissolves, it will not produce any ions. And it's the lack of ions is why it will not conduct any electricity. Any questions on electrolytes here? And there's my light bulb example that I clearly scribbled all over. There you go. On the left, no light, pure water, non-electrolyte, and obviously a little bit of salt like sodium chloride there gets you your light bulb going off brightly. So as I mentioned a little bit earlier, and just to make sure here, when we do make an ionic compound, it is always the cation and anion coming together. It's always a result of a metal and a non-metal coming together. And as we will talk about, really, the metals have a lot of properties that basically say, take my electrons. I don't really want to hang on to them. And I don't really want to take anybody's electrons. Non-metals have a lot of properties where they say, I want your electrons and I want to keep my electrons. So what happens when those two guys get together is the metals will lose their electrons to the non-metals. The result is the metal will become positively charged, the non-metal will become negatively charged. And in an ionic compound, there's absolutely no sharing of electrons. It is solely the attractive force between the positive ion and the negative ion that holds that together. So when we do put these guys together in terms of formulas, as we talked about, we do want to do the simplest way to get to zero. So here we have barium, which has a -2. So in this case, we just need one of each of them to put it together. So we get BaO as our formula. Aluminum has a +3 charge, and sulfide has a -2 charge. So when we put them together, we want to equal 0. The easiest way to equal 0 here is basically just multiply those together. That is 6. So to get aluminum to 6, we actually need 2 of these guys. And to get the sulfide to 6, we need 3 of them. That gives us a -6 overall, +6 overall. So when we put them together, we get the proper form of Al2 because there's 1 and 2 of them. S3. 1, 2, and 3 in this case. And that gives us our proper formula there. And same thing with our potassium and our phosphide here. We have +1 and -3. So we actually need not 1 potassium in this case, but we actually need 3 of these potassiums, which each have a +1 charge, gives us a +3 overall to balance out really the 1 -3 charge from our negative guy, giving us our proper form of K3P in this case. In terms of naming, the first guy would be called, these are all what are referred to as type 1 compounds. First guy would be barium oxide, IDE, aluminum sulfide, IDE, potassium phosphide, IDE there. Again, doesn't matter if you have more than one of the metal or the non-metal. It has no effect on the name part of it. Any questions on that? Now, sometimes people are taught to do the kind of switch over move where you take the charges and just move them down to get the proper formula. And that works, 90 some odd percent of the time. It does not work 100% of the time. So if you blindly do that, you will come across several that it will not work for, and you'll get the wrong formula. So it's usually best to think about just balancing out the charges. Or if you're good with like 93% of the time, go for it. Just blindly switch it over and you'll be good most of the time. Any questions on that there? Okay, that wraps up chapter 4 here. We're going to run into chapter 11 here for just a few minutes before we're done. Just give me a second. We're going to talk about sort of modern atomic theory. Really what we're going to be talking about in this chapter. Electrons, where they're as electrons sort of move from one energy level to the next, that requires a certain amount of energy to do so. And as they come either up in energy or down in energy, how that energy is either absorbed or released in an atom. So from Rutherford basically described, as we talked about at the beginning here, that an atom basically has that dense positive core, which is our nucleus, where our protons and our neutrons are housed. Nucleuses are very small compared to the size of the atom. And it's really the electrons that are on the outside flying around in that empty space. And they're really involved in most things that happen in normal chemical reactions, because if you think about it, electrons are flying on the outside. So when atoms come together, it's obviously the electrons that sort of come in contact with each other sort of first. So a lot of the idea of electrons and sort of how they transfer from one energy level to the next, which is sort of what we're going to relate most of what we talk about here in this chapter to. A lot of it was done, or a lot of beginning part of it was done by Planck. He did a lot of work with radiation, and he came up with sort of the idea that energy can be released in only these sort of certain definite amounts of energy. They're sometimes referred to as packets of energy, which is a quanta of energy. And in the case of what we'll sort of relate it to, as electrons sort of move from one energy level to the next, so as the electron goes from a lower energy level to a higher energy level, it needs to gain a certain amount of energy, right, to allow it to do that. That's an endothermic process. Energy's got to come in to do that. And if we have electrons that are in higher energy levels, and as they drop back down to lower energy levels, they actually have to release a certain amount of energy to do that, to allow them to go from one energy level to the next. And that's actually an exothermic sort of process. The way the energy is either absorbed or released a lot of times is through radiation, and really through in the form of waves, or a photon of light, which is basically a wave. So a lot of what we talk about has to do with waves, and the idea of sort of quantized energy, we'll see, I think, a picture of it a little bit later as well in this chapter, but just really quickly, is sort of like the idea of stairs. And as we walk stairs, right, we usually have enough energy to get ourselves to this step or that step, right, either going up or down, whichever way we're going. We don't usually start up a step and go, I want to just kind of rest like halfway up the step, because we'll fall. And that's sort of the idea of sort of quantized energy. The idea is this: as electrons transition from one energy level to the next, they will either gain enough energy to get themselves completely to that energy level, or they will lose enough energy to drop down to another energy level. They will never find themselves in between energy levels. And that's the idea of sort of quantized energy. You have enough energy to fully make that transition from one to the next. Just like when people walk stairs, right? Some people can do one step at a time, 2 steps at a time, right? They have enough energy to do 2 at a time, 3. Nobody does 3 or 4 at a time, but maybe. But, same thing with electrons. They gain and lose energy enough to fully transition from one energy level to the next. And as they're doing this transition, it really is sort of waves that come off or absorbed that really pack some energy associated with it. And a wave is basically a vibrating disturbance in which energy is transmitted. the bird there has the right idea at the beach, right? But as he's coming through, right, the wave is coming through, he's actually not moving, right? He's just kind of coming up and down and bobbing. And obviously, if you ever went swimming in the ocean and got hit by a wave, you know it has a lot of energy associated with it as it's dragging you underneath. And that's sort of how energy is sort of moved as electrons sort of transfer from one energy level to the next. And it does bring up the idea of the conservation of energy that we talked about, I think, in the previous chapter. You know, if there's a certain amount of energy requiring for those electrons to go, say, from the first energy level to like the third energy level, if it needed to come back down from the third energy level to the first, it would have to give off the same amount of energy to require that transition to occur. So we have that sort of conservation of energy that occurs as things transition. Some important parts of a wave, and we'll talk more about it here in this chapter. But first off is the wavelength, which is sometimes abbreviated with the lambda symbol. So if you got a wave kind of moving, that is like between two peaks, right? Or troughs, which would be the bottom, is the wavelength. Typically, wavelengths are given in meters, centimeters, and nanometers. Reminder that there are 100 centimeters in a meter. And in 1 nanometer, there are 10 to the minus 9 meters. So those are common units that are used in conversions. Frequency, although people call it V, it's new, is the number of waves that pass through a particular point in 1 second. It is oftentimes measured in hertz, like when you dial your radio to a certain frequency, like 95.5 megahertz, right? So mega is sometimes used a lot with frequency. Mega is 10 to the 6, right? Hertz is also a reciprocal second. So that is also a common unit that is used. 1 over S, a reciprocal second. So once again, a hertz is the same as a 1 over second. The amplitude is from the midpoint to the peak there of the wave. So that would be like our amplitude right there. And we can actually calculate the speed of a wave by taking the wavelength times the frequency. And if we just look at units, the wavelength is typically in meters. The frequency is 1 over seconds. So when we multiply it, it is meters per second, which is a very common sort of speed of waves that we talk about, or velocity of the waves, and how they travel are common units that we end up with. Any questions on that there? All right.